Hello, boys and girls. Welcome to Right Triangles Day 3, Take 2. Make sure you pay attention. There's a lot of stuff here, and you're going to have to stay along and make sure you listen, pay close attention. First, we're going to start out with a theorem here that says if an altitude is drawn to the hypotenuse of a right triangle, then the two triangles are similar to the original triangle and each other. I know that sounds confusing. Here's a lovely picture to help us out. So our original triangle, triangle ABC, we can see is a right triangle. Angle C is the right angle. If we draw an altitude CD from the right angle to the hypotenuse, we form a little triangle over here and a medium-sized triangle over here. All three of those triangles, the small, the medium, and our original triangle, will be similar, as you can see by the similarity statements here. Let's do an example of this. Here we've got triangle RST, which is a big right triangle with a right angle at T. If we draw on the altitude TU, we form a smaller right triangle and a medium-sized right triangle. It's sometimes easier to see if you redraw the triangles, which we've done here. Here's triangle TUS, which is similar to triangle RUT, which is similar to triangle RTS. So the small, the medium, and the large are all similar to each other because of the altitude we drew. Now, because those are similar, hopefully you guys remember, although based on those test scores I'm not so sure that you do, that we can set up proportions and solve for missing side lengths. All right, the first one we want to talk about is the geometric mean altitude theorem. Hopefully you remember geometric mean is a thing that repeats here. We talked about that during similar triangles. So in triangle ABC, if we draw an altitude CD, we know that BD over CD is going to equal CD over AD. So the length of the altitude is the geometric mean of the lengths of the two base segments it forms. So this altitude forms segment AD and segment BD. So we would have this in the place where we'd square it or multiply it by itself, and the other two things in the opposite places. We'll do some examples of these, don't worry. The geometric mean leg theorem tells us that the length of each leg of the right triangle is the geometric mean of the lengths of the hypotenuse and the segments of the hypotenuse that is adjacent to the leg. I know that sounds confusing, but if we look here, CB is going to be the geometric mean of AB and DB, which are the two segments that are adjacent to it. See, adjacent, adjacent, right next to, good. Or AC is the geometric mean of AB and AD, which again are adjacent to it. Here's an example. We've got a triangle, we've got some measurements in here. Let's plug some things in and see what we get. We want to find the value of y in no decimals. You got to reduce those radicals. So the length of the hypotenuse of triangle RPQ, which is our big triangle, over the hypotenuse of our small triangle is going to equal the short leg of the big triangle over the short leg of the small triangle. So hypotenuse over hypotenuse is going to equal short leg over short leg, or 9 over y equals y over 3. If we cross multiply, 9 times 3 is 27, y times y is y squared. We take the square root of 27, which reduces to 9 and 3. The square root of 9 is 3, so 3 comes out, and we have 3 square roots of 3. Let's get another example. Here's another triangle. Again, we want to practice with identifying the similar triangles in there. Yes, it will be on your test. So here we can see we've got 3 triangles drawn. So triangle DEF is going to be similar to triangle DGE, which is going to be similar to triangle EGF. Remember to make sure all the right angles match up. We know E is a right angle, so it's here and here, because that's the right angle. Oh, E is the right angle in the big triangle. It matches up with G, which is the right angle in the small and medium-sized triangles. So if you just match the things up, it's usually not that bad to write the similarity statement. Here's another set of similar right triangles. We want to find the value of K. So we've got the large hypotenuse over the small hypotenuse is going to equal the large leg of the leg of the large triangle over the leg of the small triangle. So we'd set that up, and 10 over k equals k over 2. Cross multiply, k squared equals 20. K is the square root of 20. 20 is 4 times 5. Square root of 4 is 2, so k equals 2 square roots 5. Number 5, this is our altitude theorem. So if we remember, that's our geometric mean. Right, the altitude is going to repeat. The other two segments are going to be on the other sides. So we'd set up x over 2 equals 2 over 5. So 5x equals 4, and x equals 5/4, or 1.25 for those of you that are fraction phobic. Number 6, we want to find the value of w. Oh, that's 8.5. Can we do this with decimals? Yes, we can. We're going to do this the same way. Segment, the small segment over the altitude equals the altitude over the longer segment. So we plug in there, 5 over 8.5 equals 8.5 over w. 5w equals 8.5 squared, which is 72.25. If we divide that by 5, we see that w equals 14.45. And example number 7, here's another triangle. We want to find the value of a. Be careful here now, this is a plus 5, not just an a. But again, the small segment over the altitude equals the altitude over the large segment. Or a plus 5 over 12 equals 12 over 18. 12 times 12 is 144. This is 18 times a plus 5. Don't forget you need to distribute this here. So it becomes 18a plus 90 equals 144. When you subtract 90, 18a equals 54. Divide by 18 and a equals 3. You can always plug it back in here and check. We'll allow that. Make sure you got these notes down. Try and look at the similar triangles and figure out where they can, how to list them all. You may even want to draw some right triangles and draw an altitude on your own and see if you can name the similar triangles. Because if you can figure out the similar triangles in this, the rest of it will be pretty easy.